What is sound? We live at the bottom of a sea of air. As with the ocean, as the farther down one goes, the greater the density of molecules, and the greater the pressure it exerts on us. The average atmospheric pressure, as it is called, is measured in many different units, but the one most people are familiar with is barometric pressure. Altitude, temperature, and weather conditions affect barometric pressure. For example, one is often associated with storm systems. If the particular pressure level surrounding us remains steady, we experience silence. The individual air molecules themselves always exhibit at least a minimum rate of motion without causing perceptible pressure changes.
Sound is produced by a rapid variation in the average density or pressure of air molecules above and below the current atmospheric pressure. We perceive sound as these pressure fluctuations cause our eardrums to vibrate. When discussing sound, these usually minute changes in atmospheric pressure are referred to as sound pressure, and the fluctuations in pressure as sound waves. Sound waves are produced by a vibrating body, be it an oboe reed, guitar string, loudspeaker cone, or jet engine. The vibrating sound sources causes a disturbance to the surrounding air molecules, causing them to bounce off each other with a force proportional to the disturbance. The energy of their interaction creates ripples of more dense to less dense air molecules with pressures above and below the normal atmospheric pressure. When the molecules are pushed closer together, it is called compression. When they are pulled apart, it is called rarefaction. The back and forth oscillation of pressure produces a sound wave.
Sound waves in air are longitudinal waves. In that, the pulsating motion of air is in the direction the sound wave travels. Physicists classically demonstrate this with the slinky model, in which a quick push on one end of a slinky will cause a longitudinal wave to travel down its length. The wave can be seen as areas where the coils are closer or farther apart from each other than would normally be in the slinky's state of rest, corresponding the compression and rarefaction of air molecules in sound. In a sound wave, the actual air molecules do not travel far, but spread their kinetic energy or force to adjacent models before bouncing back near their original position. Much like a cue ball striking another in billiards, a sound wave is also a form of a traveling wave, in that the air molecules disturbed by the sound source are unlikely to be the ones hitting the eardrum, but transfer their energy to neighboring molecules.